So, as you have seen, 2D tracking is a great way of quickly integrating flat images or movies into your footage. You can patch all kind of things, remove blemishes, cover up number plates of a car, control masks or a lot of other things just by tracking a few points. But as soon as you want to integrate 3D objects into a film with a moving camera, then you need something more. Because to get the illusion of a 3D object being tightly integrated into the footage, you need the virtual camera to do the exact same movements as the real camera. In the early days of visual effects film work, in almost any case people used a locked-off camera to put something into the footage. Because as long as the camera doesn't move, you can put almost anything into the footage and it will be very easy. But of course, as a filmmaker, you have much more creative freedom if you can have a moving camera. To solve this problem, in the 70s, people invented a technique called motion control. So they put the camera on a robotic crane arm on a dolly, and they were able to control the movement of this rig with a computer. And since it was computer controlled, they could A, repeat the exact same movement of the camera over and over again, and B, they could then use the programmed camera movement to drive a 3D camera. But as you can imagine, that technique is not only extremely expensive, but also not very flexible to use. Because you need to power that device, you have to bring it on set probably with a giant truck, you have to control it, etc, etc. And that's why in the 90s a new technique was invented, and that was match moving. So instead of bringing a giant rig on the set to control the camera's motion, the movements of the camera are being calculated afterwards. And that's what we are going to do mostly for the rest of this DVD. But how does it all work? Camera tracking is based on a technique called photogrammetry, and that is a method that is using photographic images to find out the geometry of a scene. And by finding out how the geometry of the scene looks like, you automatically get the correct camera position as well. So for example, take this object right here. So currently you don't really know how the object looks like. I mean, it probably is some rectangular shapes with this thing extruded forward, but we cannot really know how far away this object right here is. It could be very far away but very big, or it could be very close to the camera. So just by looking at this one flat picture, we cannot really know the geometry of the scene. But since we are here in Blender in a 3D program, we can just rotate the scene and thereby changing the perspective, and by doing so we can find out how exactly the scene looks like. But if you only have pictures of the scene, then of course you cannot rotate anything. I mean, it's a picture after all. So in that case you have to do something else. So let's, for example, look through one camera here. So we have this camera, and when you look through the camera, then we are in the same situation as before. So we only see one angle of the scene. So we cannot really exactly know how the proportions of this object are, if it is really all rectangular shapes, how far away that thing is, and so on. Now in photogrammetry we can pick some points here in this image, and I've done that by using empties. And then if you have a second image of the same scene, then you can measure the distances of these points. Now let's look at this from the side view. Now in photogrammetry, by picking these points, you know some certain information. So for example, you know something about the roll of the camera, of the rotation. Because with this information, the camera can only be rotated in one certain way. Because now I cannot rotate the camera without messing up these markers. So the camera can only be rotated in this way. But something that we don't know yet is the position of the camera, I mean in photogrammetry. Now let's have a look at how the image in the camera is created anyway. So you have light in your scene, and the light hits a surface, and from this surface a light ray is reflected and eventually hits the camera. Like so. So these would all be the rays that come from the points in your scene and then hit the sensor of the camera. So we know that the camera has to be rolled in one certain way, otherwise these points would not make sense. So you cannot just rotate the camera, otherwise you would just mess up the solution here. But what we don't know is the position. because I can now move the camera forward without messing up the solution here. So the only thing that I currently don't know yet in this situation is the position of the camera. Just the roll would be nailed down by these markers. But now when you have a second image of a second camera, then there's only one reasonable solution for these points, and that is what photogrammetry is all about. But how this exactly works mathematically, I have no idea. Well, actually that is not quite true. In fact, I'm doing that all day long. And I guess that even you are doing that all the day just by looking through your two eyes. Because without all these photogrammetry stuff, I mean, the point is just you have two images, and just by comparing these two images you can find out the perspective and the information and the geometry of the scene. Now let me turn off all this ray and camera stuff and just look through the cameras. So that is the image that you get from camera 1, and that is the image that you get from camera 2. And now just by comparing these two images I get a lot of information of the scene. And that is exactly the same thing that is happening in our brains all the time. And you can easily try that when you look at something in your room and close your left eye. Then this might be now what your right eye is seeing. But if you now close your right eye and open your left eye, then you would see something happening, something like that. So the scene is flipping, depending on through which eye you are looking. And when you open both eyes, you see the perspective. And of course that is the same principle that is used for stereoscopic 3D movies. So you just give your brain two separate streams of images, one for the left eye, one for the right eye, and your brain just automatically calculates the perspective. Well, now camera tracking uses the same principle. You just use two different images that are slightly offset, one right, one left, so right eye, left eye you could say. And well, since you don't have a stereoscopic input, you just take these images after each other, and thereby it is possible to calculate the geometry of the scene and also the position of the camera. And once you have these two cameras, you can easily extend that to a lot of cameras. So you would start from two images and then just extend the solution to a lot of different cameras. Now, of course, in match moving, we are not dealing with hundreds of different cameras. This is just one camera that is moving and frame by frame changing the position, and thereby you can generate these offset camera images, and thereby it is possible to calculate the geometry of the scene and also the position of the cameras. So let's try that on a real example. And I have these two images here. This is from an old factory here in Leipzig. And you can see that if I change between these images, how the perspective changes. So, and I want to bring that into the movie clip editor and see if we can get a real reconstruction just from these two images. So here in Blender, I go to the movie clip editor, click on open. And then here in the folder with my footages, I go to camera tracking, old factory, and then choose the two key images. So select the first one, click on open clip, and since they are numbered from 1 to 2, it will read as a clip from 1 to 2. So, and because it's just two images, we can also set the end frame to 2. And now we can go full screen, hit Alt A, and of course that is, well, we don't need to animate that. But well, with the arrow keys you can now switch between these two images, and we can start trying to get a reconstruction from that. So just as before in the example with this simple geometry, we have to define some marks, some certain points that Blender can then recognize on these two frames, compare them, and then calculate the geometry of the scene for that. And you need at least 8 markers so that the reconstruction can work. And these markers have to be placed in a certain way, because you cannot just assign maybe 8 markers here on this wall. That would be a total failure. Instead, you have to place the markers so that you cover up a lot of space of the scene. So for example, we can add a marker here on this corner that would then cover this middle ground here. Then we can add another marker here, maybe in the foreground, maybe that bright spot here. Then something in the very far background, that place for example. Then something here also on the same background plane, and maybe something here in the background on the floor. So now let's see, we have 1, 2, 3, 4, 5 markers. So let's add something more here on this column, which is also kind of the midground, and then also something here in the foreground, maybe that spot here. So now we've got 1, 2, 3, 4, 5, 6, 7, and let's add an 8 marker, maybe here, that bright spot here. Okay, so these are the 8 markers on this first frame. Now let's go to the second frame, and then of course we have to move the markers so that they fit to the same locations as on the first frame. So let's start with this marker right here. So we go to the second frame and then just move it over here, and of course just use this one marker and then compare if it's really the correct location, and yes, it looks like that. All right, then let's continue with that one. So on frame 1 it was here in this corner, so on frame 2 we move it up there as well. Now let's move on. This one, move it over here like so, and by the way, I'm just moving them with the G key, like grab. So go here, press the G key, move it over here, then hold down the Shift key to precisely move it, and then with the left mouse button assign that location. Then this one, I think it was this corner here, let's check. No, it was up there. Okay, then next one, this was that little hole on the column here. And then lastly, this was over here. Yep. All right, so let's see. Oh, we missed that one. Was it here? Yep. Okay, so that is that. So I believe we have now all the 8 markers covered, and now we can try to start to reconstruct the scene from that. And to do that, we need to have a look here at the Solve panel. Maybe let's collapse all these panels here because we don't need them. So we have all our markers that we need, so we can collapse that panel. We also don't need to track anything, so let's collapse this one. Okay, so what we need to do is we have to press the camera motion button to calculate the movement of the camera. But if you do that now, you will get an error. And this error tells you also what the problem is, because you have to at least 8 common tracks on both of the keyframes that are needed for the reconstruction. So keyframe, what does it mean? Well, we have here keyframe A and keyframe B. And keyframe A is set to the first frame, keyframe B is set to the 30th frame. But since we have only 2 frames in our whole sequence, let's set keyframe B to 2. So now we have keyframe A, and that is the first frame, and keyframe B, which is the second frame, and that is keyframe 2. And if you remember the theory part of this chapter, then you know that you need these 2 cameras or these 2 frames which are used for the initial solution, and after that you will extend the solution to the rest of the frames. But since we have now only these 2 frames, we don't need to extend anything. We will just use the 2 keyframes to calculate the scene. So, and now if you press on camera motion, you will get no error. You will instead get an average reprojection error of 2.7. You can also see that down here. And this value tells you that the reprojected points, so the points in the 3D scene, are 2 or 3 pixels away from the original marker. So let's have a look at the actual 3D points here inside the movie clip editor. And you can do that by going to the display panel and then enable 3D markers. So that will give you some points. So let me zoom in here. So here we have our initial track, and beside that there is this little green point, and that would be the reprojected marker from 3D into the movie clip editor. And you can see this little gap here, so it is not exactly on the same spot. So, and also you have these ones. So that is really far away, and it is also displayed as red. And if you see the name and status, then you have an average reprojection error of 3.7, which is really high. So the solution for that is rather bad. And there are a couple of reasons for that. For example, here it is really close. Maybe let's compare the two keyframes really closely. So this is keyframe 2, and if I press L to lock the view to this feature, this is now frame 1. So 2 and 1, and this is pretty close actually. But over here in the track you can see we are not really that close, so there might be also some error in the placement of the marker, so we might have to be more accurate with that. So that is one reason why we get this error, and maybe we can try to fix that by doing that more carefully. So since on frame 1 this seems to be a little more over here, this is frame 1, so let's move that also over here, and maybe that can fix that error. Okay, so now let's go over here and look at this one. This is also green, and you can see that the point is really close. So chances are that this is also rather accurate. Well, actually it's not, but well, it's always just not really that clear what is causing the error. I mean, I know what exactly is causing the error here, but in this case we can also try to be more accurate. So let's first try to fix all these problems here. So that is on frame 2, that is on frame 1, and there's clearly a mismatch of position. So on frame 1 it is here on this rather bright part of this orange point. So here that is clearly wrong. So let's press G on frame 2 and move it over here. Still not correct. Yeah, I think that's better. Alright, so now we really have to fix all these problems here. And as you can see, that can also take a while. But this is mainly because we have manually placed these features, and even without having zoomed in. So if you would really track them from frame to frame, then chances are that the position is much better, so that you won't get that much problems. Okay, so here there's also not very accurate, so move it down there. Just place it here on the correct spot. Also do that with this one. So this is frame 1, this is frame 2, so we have to move it up there, like so. So what else do we have? This one over here. This is also not accurate. Alright, I think that's it. So now that we have placed these a little bit more carefully, we can try and see if that did help in any way. So we can recalculate that just by pressing the camera motion button again. And look at that. Now we have an average solve error of 0.4, which is way better. And you really have to try to get the ASE down to something between 0 and 1. So everything that is above 1 may be wrong, but as soon as you have something that is over 2, it is really bad. Okay, so now we have that, and you can see all of these reprojected 3D markers are green, just because they are really close to the original point. So this is really below 1 pixel. So maybe this also tells you the ASE error. This is pixel values, 0.4 pixels. And if you look at the name or the status, this is 0.2 pixels. And if you look at this, this is 1 pixel and the original 3D marker. And the 3D marker is 0.2 pixels away from the original anchor point from your marker. Look at this one, this is also 0.2. So let's select everything to see if there is something way above 0.2. Oh, that one, for example, and this one too. So here we have almost 1 pixel away from the original feature. And well, I mean, this should now be clear why it is the average solve error. This is the average error on every frame for one single marker, that number here. And this is the average of all markers in your scene. And because there are some that are really low and some that are nearly 1, you get that error value here. All right, now enough of these 3D markers and names. Let's have a look at the actual 3D points. And to do that, we will shortly leave the movie clip editor and drag this down to create the 3D viewport here. Because we will need this sometime again, so we just don't want to replace that. So now we have the 3D viewport up here, and now we have to somehow translate the motion of the virtual camera to the actual camera that we have here. And to do that, you can use a constraint. So first select the camera, then go to the constraints panel, and then add a camera solver constraint. And all of a sudden you can see the camera moved and you have these little crosses here. And these crosses are the actual 3D markers, which are now rotated in a weird way, but we can easily fix that. But anyway, the point is that when you look through the camera by hitting 0, now you have these markers on the exact same position as the markers here. And now what's left for us to do is to add the background image here in the viewport. So press N, then scroll down here, then open up the background images, enable them, and add an image, set it to the camera, movie clip, and now choose the old factory movie clip. And now when you use the arrow keys to go back and forth, you can see that these 3D points are actually fitting to the camera. Okay, so far so good, but what is left is the correct rotation and position of the camera. And for that we will go here to the movie clip editor again and switch to the reconstruction panel. And then we can collapse the geometry panel, we don't need that. We need the orientation. Maybe let me drag this down so that we have a little bit more room here, like so. Okay, so we have this button set floor. Now to do that, we have to pick 3 markers that are on the floor of our scene. And for that we can use this one, and that one. And when you have selected these markers, you can make them stick to the floor by activating set floor. And when you look at this in the 3D viewport, you will find that these markers are now actually here on the floor. But still the rotation is a little bit weird, so we can fix that by picking an origin. Maybe let's use that as origin, so set origin, and that will move the camera so that this point is now here, right there on the origin. And now when you press 0 again, you can rotate around this point by setting the pivot point to 3D cursor, and then with the camera selected, hit R and then the Z key to rotate not around this view axis but just around the vertical Z axis, like so. And now we can align that, go full screen, zoom in a bit, and when you now go forward and backward, this will now stick to the scene. Congratulations! That is now your first real camera solution, and in the next chapter you will extend these 2 keyframed images to a whole sequence and then solve that.